So yesterday we talked about right angle triangle trig, where we just restricted between 0 and 90, but of course angles can be any size. So let's quick recap on how we deal with angles of any magnitude. There's our number line that we recognise. There's the unit circle. When we're talking about angles, remember we start out here at the positive x-axis, that is 0, and we go anti-clockwise around. So it breaks it up into our 4 number plane quadrants. And there's our little, well, what I call the butterfly that we draw in. And basically, it's just drawing in right angle triangles. So we can rewrite any angle in terms of an acute angle. And the acute angle will always be the angle that goes to the x-axis. So in the positions that I've placed theta there. So in the first quadrant, of course, everything's as normal because we're between 0 and 90 degrees. The second quadrant, which I call the 180 minus theta quadrant, because the angle that we would measure would be 180 degrees minus the acute angle that we want to turn it into. If we have a look, sine, which is of course opposite over hypotenuse. Hypotenuse we always assume is a positive number, being a distance, the length of the hypotenuse. So positive over positive, we know sine would be positive in the second quadrant. Cosine, though, would be negative because our adjacent is actually in the negatives on the x-axis. So we get a negative value over the positive, so it's negative. Tan also is negative because we get opposite, which is positive, over adjacent, which would have a negative coordinate there. In the third quadrant, it's 180 plus, because if we were measuring that angle, it's 180 plus the acute angle. And similar thing, we have a look at the different sides. So sine becomes negative, cosine also negative. In this case, it's the tan ratio. That'll be positive. And our final quadrant, again, if we were measuring an angle, would be going 360 degrees, but minus the acute angle we're trying to turn it into. And sine's negative. Cosine in this case turns out to be positive, and tan is negative. Now, however you choose to remember it, there's lots of interesting ways of doing it, all stations to central and all those sorts of things, but we just need to remember which one is. Now, why do we do it? I guess it originally started from back when we used maths tables rather than a calculator to work out the trig. And of course, the tables only went from 0 to 90 degrees. So if we wanted to work out the sine of 260, we'd have to say to ourselves, all right, well, which quadrant is it in? And it's in the second quadrant. So we know it's going to be minus sine, and what would be the equivalent acute angle? Well, second quadrant is 180 plus the acute angle, so it would turn out to be the minus the sine of 80. Third quadrant, minus the sine of 80, and then we'd look up sine 80 in our trig tables, and we could get the value. Of course, you don't have to go through all that rigmarole because you can just press a button on your calculator now. However, it is still important to know that for when later on we're solving our trig equations. We'll need to be able to work out those things. So tan 220, again, it would also be in the third quadrant, but this time it'll be positive, and we'd look up tan 40. You'll notice I'm doing these all to 4 decimal places because the common trig tables that we used to look up all went to 4 decimal places. Secant, there wasn't a table for secant. We'd have to look up the cosine ratio. Same as on your calculator. You can't press a button for secant. You want to work out the secant of 105. You would either go, what's the cosine of 105, and then hit your reciprocal button, or you would go 1 divided by the cosine of 105, whichever way you do it. So we get negative 3.8637. And of course, we don't have to stop at 360 either, because the circle keeps going round and round and round and round and round. So if we have something bigger than 360, we just subtract 360 until we get something we can handle. Cos 70, well, that's nice. It's an acute, so I can just use the first quadrant, same as normal, 0.3420. We can also have negative angles, and that just means instead of going around anti-clockwise, we've gone around clockwise. So if I've gone clockwise 67 degrees, I'm in the fourth quadrant. It'll actually be the same answer as if I'd gone around anti-clockwise 293 degrees. But fourth quadrant, tan is negative. The acute angle, no surprises, turns out to be 67 degrees. There you go. Tan is an odd function, by the way. There's tan of negative 67. It's the same as negative tan 67. And we get minus 2.3559. Okay. So there's a point sitting on our unit circle. Oh, actually, it's not a unit circle. The radius is 5 for this one. We want to work out the coordinates of P. Well, I can always create a right-angled triangle. They've told me that angle is 30. So simple trig. X over 5 is cos 30. 5 cos 30, but that's one of our exact values. Cos of 30 is, of course, root 3 on 2. So we get the x value is 5 root 3 on 2. The y value turns out to be 5 on 2. So the coordinates of P, 5 root 3 on 2, 5 on 2. Now what happens at the boundaries, though? That's fine for all those ones that were in between the different axes. What happens on the axes? So 0, 90, 180, 270. They're not actually in a particular quadrant. I'm going to create a triangle here. It's an interesting triangle. Its three angles are 0, 90, and by an angle sum of a triangle, the other one must be 90. So in fact, what I'm looking at there is a horizontal line. I've just turned it into a triangle. Okay. The length of my horizontal line is 1. And as it is a horizontal line, the height must be 0. And by Pythagoras, we can work out the hypotenuse, which of course is 1, because it's the same as the line. It hasn't been elevated. But now I can read off my triangle. So 0. Sine of 0, opposite over hypotenuse, oh, that's 0. Cosine of 0, that's 1. Tan of 0, that's 0. Now, 90 degrees, again, I can read off my triangle. Sine of 90 is 1. Oh, hang on, that's the same as cos of 0. 90 and 0 add up to 90. Complementary. Cos of 90 is equal to 0. Oh, that was the same as the sine of 0. Oh, 0 plus 90 equals 90. Just keeps working. Tan of 90 is interesting. When we read off, we get 1 over 0. Of course, we can't divide by 0, so that one we just say, well, that's undefined. You can't do the tan of 90 degrees. Well, 180. That's not in my triangle. But which quadrant is 180 degrees in? That's right, it's not in either. It's on the boundary between the second and the third quadrant. So now I use a little bit of logic. Okay, sine of 180. In the second quadrant, sine is positive. In the third quadrant, sine is negative. So what number is both positive and negative? Sine 180 must be 0. Okay, cos of 180. Well, second quadrant cos is negative. Third quadrant it's negative. So I certainly know it's negative, but negative what? Well, if I was in my second quadrant, I'd say it's 180 minus what? Oh, 180 minus 0. Cosine of 0 is 1, so it's negative 1. Tan of 180, second quadrant tan's negative. Third quadrant it's positive. Both negative and positive. 0. And then over at 270, we could do a similar sort of thing. We get an interesting one there, tan 270, negative undefined. Well, we just call that undefined still, of course. And then 360, we're back at 0. But, of course, the beautiful thing about this with calculators is, well, they're 1 and 0 and undefined. So you're always going to get an exact answer when you plug it into a calculator anyway. So it's not that big a deal. But the actual boundary values are really important when it comes to drawing the graphs, knowing what they are and so on. Certainly helps us plot our graphs a lot easier. So I'm going to draw sine x. I know, as I say, it goes up between 1 and minus 1. I'll mark off all the boundary values, although I've only actually labelled every one 80. I've gone a little bit crazy, up to 720, back to minus 360. When I'm graphing a sine graph, I always start at the origin. So I know it starts at the origin And then my sine graph I know goes up, because sine 90 is 1. And then that pattern just keeps going. And so I'll be going down and up and down and up. And same going back the left-hand side. And remember, we're not playing dot to dot, like when you first got your dot to dot book and you joined everything with straight lines. It's a nice, smooth curve. There it is, y equals sine x. Now what can we tell from here? I can see straight away that the domain is all real x. There's no breaks in that curve. The range is -1 to 1. I can also see that its period is 360. Now remember, period when we're talking about trig graphs means how far do I have to go until I'm repeating myself. And you could pick any point on the graph. And by repeating, it has to be going in the same direction as well. Because just say I did pick the origin, it looks like it only took 180 to repeat. But at the origin, I'm going up. At 180, I'm going down. So I haven't actually repeated the value yet. It's not till I get to 360 that I'm going back up again. So you can pick any point on the sine graph, go 360 degrees, and you'll be at the same y value. Okay. It is an odd function. It has rotational symmetry. So another tool we can now use is we can say, oh, well, hang on, I know the sine of negative x will be the same as the negative of sine x. So I could use that relationship in problems. All right, let's draw the cosine graph. Now, we know it's very similar to the sine graph because co meant complementary. So it is the complement of sine. Has something to do with 90 degrees. So what I'm expecting to see here is a sine graph and something to do with 90 degrees. A shift. Which way? Well, let's see. Cosine of 0, remember, was 1. So I'll plot up there. And then I went down, and then that pattern continued. So down and up and down and up and down and up, and on the left-hand side as well. And there it is. So, in fact, we have shifted our sine curve 90 degrees. Which way? To the left, isn't it? Yeah. So to the left, and we have the same graph. And, in fact, if you were to place these on top of each other, you would get the ABC symbol for channel 2. And that's, in fact, where it comes from. Because the reality is, it's not that they've placed a sine on the cos. It's, you know, when they oscillate the curves and it looks like it's going back on each other, and that's what the ABC symbol is. Okay, domain. Well, it's the same curve, so you expect the same domain. All real x, you expect the same range. You would expect the same period. But now, it's no longer an odd function. We have an even function. We've got reflection in the y-axis. So we could, for a cosine function, go the cosine of negative x is in fact the same as the cosine of x. We could use that relationship in problems. Well, I can't do sine and cos without tan. Tan's a little bit more interesting. There's no amplitude with a tan graph. It keeps going up to infinity, down to minus infinity. So I haven't bothered labeling anything on the y-axis. But I would start at 0, and then we have these undefined. So when we're graphing undefined, we have an asymptote. And that pattern just keeps going. So there, asymptote, x-intercept, asymptote, x-intercept, asymptote, and so on and so on. Now be careful when you draw your basic tan graph. The temptation, and what a lot of people do, is to make it look like a cubic. But it's not. It comes through the origin at 45 degrees. Okay? It doesn't come through flat like the cubic. So you should be drawing it to come through at 45 degrees. And then that shape basically repeats in between all the different asymptotes. There we go. So what can we tell from this one? The domain's a little bit more interesting because we have all these asymptotes. So a way of generalizing that, so I don't have to say, oh, except x equals 90 and 270 and what's the next one? 270 and 450. Thank you. 450. And in the back in direction the other way, I could have said negative 9. In fact, there would be an infinite number of them if you think about it. So it would take a very long time to list them all. So we generalize it. So basically, I'm saying every asymptote's at 90, but every 180 degrees before and after, there will be an asymptote. So I'm saying multiples, because I've specified k as an integer. So multiples of 180 before and after, we'll see an asymptote. So that's how I write the domain. Range, of course, is a lot easier. All real y. The period for this is only 180. Only takes 180 degrees to repeat. It is also an odd function. It has rotational symmetry. So the factor we could use for tan would be the tan of negative x is the negative of tan of x. So again, that may help us in problems. Another graph. Let's have a look at one of the reciprocal graphs. And we're going to draw cosec. Cosec is, of course, the reciprocal of sine. And earlier, a couple of weeks ago, I think it was, we talked about drawing reciprocal graphs, 1 over the function x. So let's do it with our sine graph. There's the original graph. I've just dotted it in. Sine x. What did we say? We said everywhere there was an x-intercept would become an asymptote. So we know we're going to have all these asymptotes on our graph. Now, it goes up to 1, down to -1. Well, 1 was a very important point, because, of course, if you turn 1 upside down, you still get 1. So all of these peaks are still there at 1 and -1. But the difference is, we said when the original graph was below 1, the new graph will be above 1. So it will turn, instead of going concave down in this section, it'll be concave up. We've got asymptotes. We know we've got to bend towards the asymptotes. So we'll get U-shapes all the way along. So there's our cosec graph. Sec graph would look similar, except it's shifted 90 degrees to the left. Cotan, when you do that one upside down, becomes quite interesting, because your x-intercepts become asymptotes, but your asymptotes become x-intercepts. And it looks like you've just reflected, but there's a bit of a shift happening as well, but they end up going in the opposite direction, those curves, when you do the cotan graph. Okay, so 4D we shall have a go at.